Remember, so far in Chapter 6, we've been discussing continuous variables and continuous probability distributions. There is a special situation where we can use the normal distribution to approximate a discrete binomial distribution. Remember, a binomial distribution is discrete with only two outcomes, success and failure. So we are looking at a discrete number, a whole number of successes. When the number of trials n in a binomial distribution becomes large, we can approximate the binomial with a normal distribution. There are simple rules to determine if n is large enough. We also remember that to calculate probability for a normal distribution, we need the mean and the standard deviation. Therefore, for a binomial, we calculate the mean as n times p, and the standard deviation is the square root of n times p times 1 minus p. So how do we use a continuous normal distribution to represent a discrete variable, a whole number? This requires us to add and subtract a correction factor around the x value of interest, remembering that x is a whole number. In a few slides, you will see graphically how this correction factor comes into play. But for example, if in a binomial distribution we are interested in the probability of x equal exactly 12, then we will add a correction factor of 1/2. So we're looking at the probability that x is between 11.5 and 12.5 on the continuous normal distribution. Let's follow an example. This is a binomial problem. Given that we want to calculate the probability of x equaling exactly 12. So we can calculate the mean and the standard deviation of this binomial, which you see below. Mean is 10, the standard deviation is 3. To represent this graphically on a normal distribution, we are looking at the interval just around 12. So adding that factor, it would be the interval from 11.5 to 12.5. Now, remembering the last lecture on normal probability, we can calculate the probability in any interval on a normal distribution using the standard normal distribution or the z-distribution. So, using the standard normal or z-distribution, first we will calculate the probability of being less than x of 12.5, which is less than the z-score for 12.5. We will also calculate the probability of being less than x equal 11.5 by calculating the z-value for 11.5 and then finding the probability from the table. Given those two probabilities, we can determine the area under the standard normal curve between those two z-values or those two x values by subtracting the two areas. Gives us a 0.1052, or just over a 10% probability of being between x of 11.5 and 12.5. Since we are representing a discrete probability, this 10% is the probability of being exactly 12 in our binomial. As I mentioned before, the exponential probability distribution is described in our text and introduced here. We will not address it in this course, but the concepts for calculating probability as area under the curve is exactly the same for an exponential as it was for a normal or a uniform.